Welcome to Learning Machines. Thanks for Bloomberg for sponsoring us. Today we are excited to have Jonathan Berant with us from the University and Google DeepMind. Jonathan works on made significant contributions in semantic parsing, more recently in LLM post-training. His work was acknowledged by multiple awards at ACL, EMNLT, NACL, and ICLR. Personal trivia fact about Jonathan. My first research project, I probably don't remember that, was under his mentorship. It was a complete failure. I didn't do anything for the protocol, nothing even ran an experiment. I don't remember what it was about. Part of speech tag. Anyway, thank you, Jonathan, for joining us.
All yours. Thank you. Thank you for inviting me. I haven't given this type of talk in a long time. So I did something similar to yours. Oh, this doesn't work. Come on. It has like a battery. Oh, yeah. So this is, thank you, Yoav, for inviting me. This is Yoav and I in 2010 in Seattle. I think it was Thanksgiving. It was like 14 years ago or something. Yeah, I really like. I'm really glad you invited me. Like, I wanted to use this photo forever. So. Okay. Oh, sorry. And yeah, and at the time we were like, NLP was this like fringe thing at like the outskirts of computer science, and we were doing really strange things. And Yoav really liked this formalism called CCG. He has like a very famous tutorial on it, and I almost doesn't really. And I was doing intelligraphs. graphs. Let me just like. So I was doing intelligraphs, graphs, but that was in 2010. Anyway, moving on. As we all know now, people when they build language understanding systems, there's like kind of like a conventional pipeline for how to do it. First, you pre-train on a lot of raw text. Then you do what's called like instruction tuning. So I'm assuming most people know this, but I'll just say it anyway. Where you have like these training examples where you have like an instruction and an input and you need to produce some output and you do standard supervised fine tuning on that. The data is either human labeled or synthesized from some model or something. And then the last step is alignment, or sometimes it's called post-training, where you basically try to take like a model that now has a lot of knowledge from the pre-training stage and can like follow instructions from the instruction tuning phase. And you want to make it behave in certain ways, to be factual, to be helpful, to be safe, to be less chatty, more chatty, and so on. And this is typically done by using like samples from the model and annotating them in some ways. And I would say like in general, again, here it's really hard. Okay. Just like very funny. If this would, okay, it works. So here I'm like being blinded by this, but I'll just like make do with what we have. So the first two parts, I think, are relatively stable in some sense, right? Like, I don't know, if you think about like how people do this across organizations, it's more or less the same thing. Instruction tuning, you do like, next word prediction and optimize maximum likelihood. But it seems like the post-training part is more of a Wild West still. Like, I don't think there's like completely clear, like what's the right way to do post-training. There's a lot of papers on that. And there's a lot of like research going on in general, trying to like find like a more kind of like canonical principle way to do this part. By the way, feel free to ask questions during. So I'll try to kind of like broadly categorize the methods. Like again, this is like a very broad categorization. And also one disclaimer, to be fully honest, in the last five months, I've been working on very different things. So I haven't followed all of the papers, and there's been like a lot. There's like a water. Oh, that's great. There's like a waterfall of papers, as you can see, that I like Yoav, I generated this image somehow. So this will be like more of a high level of like the way that people do it. Right now, by the way, I'm doing some multi-agent stuff for pragmatics if people want to talk about it later. So, one thing you can do to align your language understanding system is to not train at all, just to use in-context learning, use prompting, use some examples. There's a little bit of work on that, kind of like hedges on like the understanding that, or the assumption that like alignment is superficial in some extent, that the main thing that you're changing is like the format and not teaching like new skills. All of the skills are from the pre-training. And there's been some success at that and good results. most evidently in this paper from UW, but it is limited like in how much you can do just by like prompt engineering and selecting examples. And in some cases, it's not like you cannot obtain like the goal, the alignment you would like to achieve. More common are what's called on-policy or online alignment, or off-policy and offline alignment. And I'll briefly describe those, like both on-policy and off-policy. So on-policy is represented mostly by what's typically called RLHF methods that are RLHF-like. And like the main property of these methods is that you're training continuously unsampled from your current model. Okay, so that's what I'm saying on policy. I mean that during training, you're actually sampling from your model and somehow getting feedback on that and iterating. So just to go over this a little bit more slowly, you have some prompt and some policy. You generate some generations from them, maybe one, maybe n, I don't know. And you have some method to annotate those to say which ones are good or which ones are bad to some extent. And because you're annotating them online, then this needs to be done automatically with some model. Then you get your training batch, you train, and you iterate. So this is like on-policy methods. And then there's what's called like off-policy or offline methods, where there's like more separation. Like you first have some policy, let's call it policy row, where you generate some data from this policy, and then you annotate. Now, because you're annotating offline, you can do it either with people or with models, however way you want. You get a training data set. And now once you have this data set, like you can train your policy in however way you want. This policy can be initialized from a row, it can be initialized from somewhere else, but it's like you get some distribution of data, and then you take your policy and you train it using like standard supervised methods, and you get your policy pi. But the main distinguishing property is whether the samples that you're training from are sampled from the current model that you have, or whether they're like from some different distribution that you used before. And again, I think it's kind of like difficult to like align the mental model of where the universe is right now because there's so many papers. But in my head, my mental model is that overall, it's been shown that if you want to get best performance, then offline methods seem to be suboptimal, or they underperform compared to online methods. And there's been many, many papers, I think, that show this to the extent that it's now pretty convincing. Here are some examples. This was a paper from DeepMind, from some people, DeepMind a while ago, where they tried to do this relatively apples to apples comparison between taking the same data and like changing whether things are on policy or off policy. And they show like a pretty considerable gap in favor of like online on policy methods. Some theoretical work from CMU, where they also show that theoretically, due to problems of coverage, like if you're off policy, if the distribution you're sampling from the training data doesn't cover well like the space of possible outputs, then you might get subpar performance. Here's another paper from people at Stanford, where they also find that you get lower performance if you use off-policy methods. Notably, like some of the authors are the authors of DPO, so maybe that also says something. And also, I think folks at AI2 had some papers where they show that in terms of performance only, then you get better performance from on-policy methods. And there's been also some work on like trying to kind of like pinpoint what exactly is the reason. I'm not sure it's like 100% well understood. Maybe we can discuss this. But like in the paper from Stanford, they kind of like say that if you have like a reward model, imagine like you have a reward model that says whether an output is good. So on the right-hand side, so if like the areas of high reward have high probability with respect to like the model that you're starting with, so PyRef is like the language model policy that you're starting with, and you're looking at the distribution over generations, and if like the high reward regime has relatively high probability under the reference model, then these off-policy methods will do well because they can like cover well enough like this regime. But if it looks like this, where high reward generations have very low probability under like your reference policy, then when you're sampling from your reference policy, you're not going to get good enough signal to kind of like get like the best possible performance. Okay, so that's like potential reason, and they have some experiments on this. But still, like offline methods are still very popular. They exist all around us. They've been used, like you see here. I think they're what's used in Almo, and also they've been part of the training loop in the Llama 3 tech report because they have a lot of advantages. You know, they're very simple. You don't need to train a reward model. You're not using PPR. You're like kind of like more standard supervised methods. And they can also be put in like this kind of like semi-online loop, right? Where you get some data, you look at the data, you annotate the data, you make sure the data is fine, you augment the data in various ways that you find are useful, then you train with DPO, and you kind of like repeat. And this seems like to be pretty successful. So in general, they consume a little bit less compute. So I think offline methods still are very popular and also are being used quite broadly in the community still.
I think this has come up in several talks in a row. I just want to make sure I understand how you're using these terms. So other speakers we've seen have referred to this as offline on policy. Do you dislike that term, or how do you?
Yeah, I mean, I never can remember like the definition. Can you say what you mean by those? And I can say.
So I guess the argument is because it's iterative, it's still on policy, but every step is offline. I know that's a weird distinction.
That sounds fine.
Okay. but in your previous slides, you were using them kind of synonymously, or should you care?
What I was saying, I was saying online off policy interchangeably.
Okay.
So you're saying online off policy because you're kind of like updating, but off policy because it was from a different distribution.
I was saying offline on policy. I know it's like confusing because every update step is with data in an offline way.
Yeah.
Because you're iteratively doing it, you're kind of trying to stay more on policy. But maybe it's just confusing, or maybe
it's confusing to me.
Okay. You're not trying to make a purposeful distinction.
No.
Okay. No. That's good. Thank you.
Okay. Yeah. So this is what I said. So again, just like to point out that there's like variance across the methods with which people do post-training, which I alluded to at the beginning. So this is like from the Llama Tech report, and this is like Sasha said, is like some combination of online and offline with some noun following it. And on the other hand, if you look at papers from Google DeepMind from this group that I showed before, they do something much more online, right? So they have this bond method where you start from like an initial policy and you're iteratively kind of like trying to match the distribution of your reference policy with like some best event policy. And you do this iteratively. And it's all kind of like this very delicate, I mean, this is like not the simplest method, I would say, but there's like a very delicate trade-off between, on the one hand, trying to explore better policies, on the other hand, kind of like not drifting too far and making sure you're like in a reasonable regime. So they have kind of like this exponential weighted averaging and some anchor that you always kind of like regularize towards. But these are like very, very, very different pipelines. One more on the offline side and one on the more online. Okay. So this was just like, I don't know, high level, the way I think things are done right now. So moving on to problems. So I think the key problem that people are talking about in like the online case is reward over optimization. So as we saw before, when you're doing online learning, then basically you're sampling from the model all the time, and you have some reward model or something, some model that tells you whether what you did is good or bad. And at some point, it could be that, like the reward model will say that something is good, but in actual life, it's bad. Like the reward model has some blind spots, and you're kind of like driving your policy out of distribution, right? You have your initial policy, and maybe you collected data for that policy, and maybe you trained a reward model on that policy. So maybe the model that you're using for kind of like judging if things are good or bad are fine when you're sampling from like the reference model that you started with. But as you're aligning more and more, then also kind of shifts its distribution to new things, and the reliability of the reward model kind of decreases. And then there's more probability that you will have divergence between what the model thinks are good outputs and what are actually good outputs. And people have reported a lot of like these phenomena where, maybe models think that longer outputs are better for some reason. Maybe models think that emoji are very good because like the more I add emoji, the reward model is happy. Maybe it's good to use certain formatting and so on and so forth. Yeah, and this is like from Llama 2 where basically each point is, I mean, don't, more or less the point is that every point here, they re-annotate preference data and retrain the reward model because they don't want the reward model to be out of distribution with respect to the policy that's generating the data, right? So there's this problem that the reward model kind of like gets inputs that are out of distribution is a problem, and you kind of like re-annotate and like realign the reward model to match the distribution. So this is like a robust problem. In the offline case, there's been a lot of talk, or after DPO came out, pretty quickly people noticed a problem. And the problem was that when you train, you see that the probability of both the preferred responses and the dispreferred responses in the training data, the probability of all of them go down. And, you know, maybe that's not a problem if like probability mass moves to outputs that are good. But in many cases, what you find is that they actually move to outputs that are, I don't know, catastrophic or really, really degenerate, at least to some extent. So this has been recently termed by Rosine et al. At Princeton as like likelihood displacement. It's like overfitting, but like it's like likelihood displacement where like probability mass, when you generate from the model, is concentrated on outputs that are very, very bad. Does that make sense? And that's another robustness problem. So my plan for today basically is to talk about two recent works that I've been involved in at GDM. I'll talk only about work at GDM because that's where I've been in the last year and a half. One on trying to make, and the title of the talk is towards robust post-training because I don't think we're there yet. But one on like improving the robustness of online alignment through reward ensembles. This is work that we presented at Column very recently. And the second is about doing more robust offline alignment through reward distillation and pessimism. This is under review right now at TMLR. Was unfortunately rejected from NeurIPS, and then we'll have some discussion. Cool. Any questions at this point? Great. So this is the first work, helping or hurting reward model ensembles mitigate or not eliminate reward hacking with a bunch of folks at DeepMind, and Jacob is the first author, Jacob. Cool. So let's do just like a quick background on like RLHF. Again, I assume this has appeared here already in the past, but just to make sure. So this is like the image from Stinnen et al. 2019, learning to summarize, if this like makes you remember what that is. But in a nutshell, this is like a two-step process or a three-step process where you get reference data. That is for certain prompt X, you get two out or multiple out ranked outputs where some of them are more preferred than others. And once you have this data, you train a reward model. So you find some reward model that maximizes this. So you sample from your preference data, and you want to make sure that the probability of preferring the preferred one is much higher than preferring the dispreferred one. So like this log probability of like the difference between the two reward models, it's like a Brad and Terry model. And once you have a reward model, you can use that as a target, right? So now you can maximize your expected reward using PPO. And because, you know, the reward model might have blind spots, and because the initial model it's actually pretty good, but like it's good. You don't want to like override all the pre-training, then you add like this scale regularization. So, you know, samples from your model need to have like high enough probability under the initial model. And again, very quickly, as I said, people have noticed this problem of reward over optimizations. There's many, many works. Here's like a sample that in general, let's not go over them one by one, show that if you have like several reward models or humans versus reward models, then as you optimize towards maximizing the reward of like your driver reward models, the one that you're actually using in your training loop, then as you're measuring your reward with respect to some other reward model, or with respect to the truth, or with respect to like what humans think, at some point, like the gains diminish or potentially even decrease. Cool. So how do people try to mitigate reward over optimization? Again, there's a lot of approaches. I'm not going to cover all of them, but at a very, very high level, you can try to limit your exploration, like try to stay relatively close to your reference model. This is what the KL term does. And there's also other work that have been proposed on like replacing the KL term with some other divergence metric, like, I don't know, like other part like chi-square or something. There's also been like a line of work where you try to control your training data. So you can imagine that maybe your preference data might have some correlations that are spurious between the feature and the label. So you might like think in advance and say, well, I don't want length, to be a factor in deciding whether the quality is high or low. So I'll control for that. I'll rebalance the data or something like that. And there's been some work on that, and that's also could be successful. But I think by and large, it doesn't like solve the problem. And also you kind of like need in advance to think what are the things that you want to control for. You can like iteratively try to control for them, but it gets like combinatorially hard. And more generally, you can just try to have better reward models. Just try to find like much, much better reward models that have as little possible vulnerabilities. And one kind of like approach that I'm going to focus on in this work is to use ensembling. Some sort of ensembling, like you see in these refs, there's more, or maybe some model averaging that was also proposed as a way to kind of like get a better reward model. And the idea is that, if your reward model has some vulnerability, maybe there's another reward model that doesn't have that spurious correlation, doesn't have that vulnerability. If you ensemble them or do something smart with them, then maybe like the errors will cancel out, and then you'll get like a better outcome. So that's at a high level the idea. I don't know, this is like a stupid illustration, right? Like if you have like a two-class classification problem, then you have many possible separators. But if there's many that kind of like agree with the data, then there'll be like these large regions where they disagree, and there will be high uncertainty. Maybe these are like, maybe you should not really go towards these regimes. Cool. So our work is very kind of like empirical investigation. This blue square that appeared. I did that inadvertently. What we want to do is to experiment with multiple reward ensembles using two alignment techniques. One is RLHF, which I already described. And the other is best of n. It's like an inference time re-ranking. Again, I assume this has appeared in the seminar already, but like in a nutshell, you have like your initial model, pi ref, you sample n outputs, and then you score them with a reward model, and you choose the one that has the highest reward. So this is another way to kind of like shift your distribution towards like high reward regions. And so we're going to build these multiple reward ensembles and do experiments on how can you try to mitigate reward hacking on 3 tasks. So we'll experiment with 3 tasks. One is a dialogue task where you have like a helpful assistant, hopefully, and you want to make it as helpful as possible. One on summarization, you want to get high quality summarization. This is the TLDR benchmark. And one is like you want to get a summarization system that is factual in the sense that the summary is entailed by the document, so you don't hallucinate. So we experiment with these tasks, and we're going to try to use 2 types of ensembles. One is what we call a fine-tune ensemble, and the other is what we call a pre-trained ensemble. A fine-tune ensemble means that we're going to take a single pre-trained model. They're going to be from the T5 family, like you see here, and we're going to fine-tune 5 times. And this is a fine-tune ensemble, just changing the random seed. Nothing changes except for the random seed. And we also have pre-trained ensembles where we take a randomly initialized model, like the parameters are randomly initialized, and you pre-train 5 times for both T5 base, T5 large, T5 XL. This is like our attempt to just run the code that was used to train T5. And you just change the random seed, right? I think that there's like on C4, it's not even a single epoch. So the data is not identical. But like you just change the random seed. And then you do also, so you can also fine tune again. So a pre-trained ensemble where the pre-trained seeds are different, fine-tune ensemble when the fine-tune seeds are different. And then we're going to check whether there's reward hacking. How will we check if there's reward hacking? by using like a better model, right? So this is like what a lot of people do and say that this is correlated with humans, but take it with a grain of salt, where like a bigger and better reward model will say whether things are actually improving or not. So you'll get the reward according to the model you're using for training, and also you get the reward according to the model you use for evaluation, and that's going to be like a better, bigger model. Does the setup make sense?
Jonathan, what are you training the reward model?
So there's 3 tasks. So there's preference data for helpfulness and for TLDR. And for summarization, it's like an NLI data set.
Okay, so it's like 3 separate.
Yeah. Yeah. So you have at the end 75 reward models, right? You have 5 pre-trained seeds, 5 fine-tuned seeds, 3 tasks. So there's 75 reward models at the end. By the way, we did release publicly the pre-trained, the 5 pre-trained models. So I don't know, 5 times 3 for these 3 sizes. So if you think that it would be good for you to have like pre-trained models that the only difference is the random seed at pre-training and want to check like the variance and stuff like that, then you have those are online. I think this could be like a useful artifact if you want to see like how different are things when you have multiple pre-trained models changed only through the random seed. Yeah.
Just out of curiosity, like, this task is kind of just a regression task, right? Like these values, they kind of giving scores. Like, is there a way to evaluate it without a generator, or like, are you think the only kind of useful case when you're going to have the generator in?
Well, you can check like on the validation set, like what's the performance, and we do that. You can check like on some out of distribution. And I think there's been some work saying that it's not that, I don't remember this exactly, but that it's not always the case that the reward models that are better on like an IID validation set are necessarily better for like RLHF. I don't know. That sounds weird to me, but I have seen some work on that.
There's like some difference between like how good you are on static data and then how exploitable you are by a like generator.
I mean, I don't know if I believe that, but that is a claim that is made. But specifically, like for the test, we only have like this IID setup, right? Like I will show results on like how good is the reward model in terms of generalization to an IID validation set. But like the point of RLHF is that you're kind of like by design shifting out of distribution, and that effect can be shown in this generative setup.
How much variance do you expect to see between each of the 5 random seed models in each family? Like,
Okay, let's look at that. Let's look at that. That's yeah.
5 model.
And not what? This was completed at the end of 2023. But like, which one would you have done? I mean, we could have done Palm at the time. There was no Gemma. There was no Llama. We would have done Google stuff.
Maybe I'm more asking about why parameterized with encoder decoder.
What?
Maybe I was more asking why you choose to do encoder decoder as opposed to encoder.
I mean, I think for like, these are reward models. So the policy, the generator in some of the tasks is going to be like a decoder only Palm 2 model that we had at the time. But for like the task of just like assigning the reward, we used like, it's pretty reasonable, I think, to expect that like T5 would be good at saying whether like a summary is good or whether like, whether it's factual. I mean, I don't have like a strong reason to suspect.
You're just thinking the encoder of the T5. So
no, encoder, no, like just the usual thing. Yeah, like you feed it the way it is. We didn't change the architecture at all. So like the Y part will be like, there will be like a causal mask there. I mean, I don't view, like, I think these are good enough models. We also see their performance. Maybe other models will do better. Not sure. Like they're roughly at human agreement. Like, cool. And like it was asked by, sorry.
Cole.
Yeah, we're pretty interested in the question of whether like, what's the agreement of the models, IID versus like, as you train and move out of distribution, what happens to the agreement between reward models? So that's going to be the center thing. I'll try to keep time. I see that I'm going pretty slowly. Okay. So this is basically what I said, the pre-training part, we pre-trained 5 times. And then this is like the 3 times 25 models. And the policies for summarization tasks, we found T5 to be sufficient in quality by just like looking at it. For the helpful dialogue task, we found that it requires a lot more knowledge. There's questions like I don't know, what are common butterflies in Oregon or something. T5 doesn't know, but Palm 2 does know. So yeah, we need to understand. And one methodological thing that's like, just to point out that we're going to have these plots where the x-axis is KL from like the initial policy, and the y-axis is reward, like how good it is. To get these plots, we don't just like trace like what happens during training, because we found this like underestimates the true possible performance at a certain KL. So we just like change the regularization coefficient and train to convergence to make sure that for some certain KL, you're trying to get like to the best possible reward. We found that to be important from the perspective of like looking at plots and seeing something. Okay. Cool. So first, I just want to show this underspecification property. Underspecification means that the reward models agree in distribution, but they're underspecified out of distribution and disagree more and more as you run RLHF more and more. So this is like the in distribution performance for like the models and the tasks, T5 base large, extra large. You can see the standard deviation is quite small. So all the models, regardless if they were pre-trained with different seeds or not, get more or less the same performance. I mean, I didn't check like per instance, but like the overall performance of all models is quite the same. And you can see how it improves as the models become bigger. So this is like IID. These models tend to have similar behavior, okay? And now we want to convince ourselves that as you move out of distribution, the behavior changes. So let me try to explain this plot.
Jonathan, did you look at the correlations between the models? Because it's like performance is one measure to look at like how they are similar. But
In distribution, we didn't do that. But I'll show some out of distribution plots soon. So in the next slide. So here on the x-axis, you see something that's like KL, because like how many, this is best of n. So KL is log n minus 1 roughly. So this is, you can think of it as this is KL. It's like also an exponential scale, in logarithmic scale. So the green curve is basically what the model that you used for ranking thinks. Okay, so I have some outputs, and the reward model chooses one of them, and it declares what was the reward. So this is the green curve. Okay, so you're choosing one of the models to choose an output, and it has some average reward across stuff. And the blue and the orange ones are what other reward models think about this choice. And what you can see is that there's a gap, right? So the original model that was used for choosing the output, that model thinks things are great, but the blue and the orange one thinks it's not as good. It's like substantially less. And more than that, you can see that the disagreement for the pre-trained ensemble is higher than the fine-tuned ensemble. So the reward models that were trained from a different pre-trained seed, they dislike the choice of the initial model more, basically. So and the gap kind of increases. So this is like evidence number one. As you align more and more strongly, different reward models start to disagree with each other more. This is a similar plot relates to Yoav's correlation question with RLHF, where you take your policy and you sample 5 outputs per prompt. And like as you're training RLHF, you're sampling outputs, and then you check what's the rank correlation between the different reward models in like ranking these outputs, right? So there's different rankings for 5 things, and you can compute like a rank correlation between them. And we see 2 things. The first thing is that the correlation, oh, I think the color coding switched. I'm sorry about that. Like for different pre-trained models, when the reward models are trained from a different pre-trained seed, then the disagreement is much lower. So there's a lot less agreement or a lot more disagreement when the reward models do not originate from the same pre-trained seed as the original one, compared to when they originate from the same one. And RLHF makes this worse, right? Like as you're running RLHF more and more, the disagreement increases more and more. Okay, so this was meant to convince you that the process of alignment makes reward models disagree with each other more and more, And so, if you use one of them, it might be exploitable in some way. And maybe some other models will not like that exploitation. Cool. So if you know that, then a natural thing to do is to ensemble. You're saying, okay, one of my reward model has this exploitation. Let's try to ensemble them. And maybe the errors will cancel out and things will be great. So this is like an illustration. You get some context X and you sample some output Y. This is like the true reward. And you get like a bunch of rewards and you average them. You hope that the average one will be closer to like the true one compared to each one of them individually. So one of the things that we did in this work is like experiment with different possible ways of aggregating the reward scores. Our initial hope was that aggregations that take uncertainty into account, that kind of like look at the variance, will be good. So things like mean minus standard deviation, right? Like the more they disagree, then you should penalize the reward more, right? You should not like it if they disagree. In practice, we didn't see something compelling enough to like actually show results on this. It seemed like that averaging the rewards it wasn't always the best, but it was always close to being the best in some sense. So I'm mostly presenting mean, like, I don't know, maybe someone else will find that you can use the variance in like smarter ways. But we didn't find that, unfortunately. So here are the results again. This is the best of n. And I mean, the plots are small, but the differences are significant. And as you might expect, like the green curve is when you're using just a single reward model for alignment. The blue curve is when you're using an ensemble, and the members of the ensemble all originate from the same pre-trained seed. And the orange one is when you have different reward models that have different pre-trained seed. So everything is identical. The only thing that's different is just like the pre-trained seed, and you get like considerable gains in performance. Yeah, so pre-trained ensembles are more effective than fine-tuned ensembles. Cool. Maybe I'll go a little bit more quickly. These are the results with RLHF, with PPO. And again, left and up is good because you want to get low KL and high reward. And in general, you can see that the orange is more to the left and up compared to the blue and the green, which means it gets higher reward at lower KL. Yeah, this is what I said. Pre-trained ensembles outperform fine-tuned ensembles. It's worth saying that you still see reward hacking, right? Like things are not solved, right? Like when the reward model is small, like in the base case, when it's T5 base, and the policy is like stronger, it's T5 large in this case, then even with ensembles, the true rewards will decrease. So reward hacking remains, maybe delayed, maybe less severe, but it still exists.
Sorry, I missed the distinction between fine-tuned and pre-trained here.
What?
What's the distinction between pre-trained and fine-tuned ensembles?
Okay, this is important actually. It's whether the ensemble is comprised of 5 reward models that started with the same pre-trained model and were fine-tuned 5 times on the preference data, or whether it's 5 models that were initialized randomly, pre-trained 5 times separately, and then fine-tuned 5 times. So like they differ so the pre-trained part was different random seed. The point is like when you pre-train separately, you get more randomness, you get more diversity, and hopefully like they're less correlated with one another. That was the hypothesis. And that's true.
But it's much more expensive, right?
Yes, but we released them. So you don't have to.
Yeah, this side.
Sure. Just ping me later. What?
Part of it is because part of the pre-trained benefit is because you are not going over all the data. So the data is different.
It's same distribution, but not identical data. We don't have an appellation on same data, different order.
But not enough compute?
Yeah, I'm in the foundational research unit. We're very like you guys.
That's like
Cool. Yeah, and just note, like this leads to much higher KL compared to best event. Best event is like, it's like 3 or something. And this is like evaluating with like what palm to large. At the time, that was like huge. Cool. I'm just gonna continue because to have time. But importantly, they don't solve things. So this is like qualitative analysis that I think is pretty interesting. So if you actually look at the data during RLHF, what you see that these models are still correlated in their errors. Like the hope is that they're not correlated with the errors, but they are correlated in their errors. So what we noticed back then, I think now it's well known that like these many times the reward models like the outputs to be like bulleted lists. I don't know, do you know that already? Yeah, cool. So at the time I didn't know that, but you see that a larger and larger fraction of the outputs become bulleted lists. And this is like, the blue one is like the ensemble. When you do RLHF with the ensemble, the pre-trained ensemble, and the orange one is if when you do RLHF with each one individually, and you can see like 3 out of 5 inherit have this property, and the ensemble inherits this property as well. Okay, this is for TLDR. There's like these 2 phenomena where things become longer. This is pretty well known. So you can see like the orange are different 5 reward models, and the blue is the ensemble. And there's a lot of copying. It starts like copying verbatim stuff from the input. So this is the longest common subsequence, kind of like increases, and you can see like what it looks like. There's this effect. The dashed lines are like the statistic on the preference data. So it's much, much worse than the preference data, right? It doesn't match the preference data at all, right? Cool. And this is for factuality. If you just optimize for factuality, you get like almost empty strings. That's what happens. Like it just, the empty string is entailed by everything. Cool. So this is this part. So we did this investigation where the hypothesis was the reward models are unspecified out of distribution. That is true. Then you might think that ensembles should be useful. They are, but they don't solve things because they have correlated errors due to like the data that they're trained on. And so maybe, people can think of other methods, like instead of like using ensembles, maybe estimating the distance from the training data. I find all of this to be kind of like, there is some ceiling effect because you want to kind of like explore out of distribution, but then you add all these regularization to like make it not to out of distribution. So it's kind of like, becomes pretty finicky. But I think there was also some work on like using like Gaussian process stuff to kind of like estimate the distance of your outputs from like the original training data. Like the representation of the reward models versus the representation of the preference data, also leading to some limited gains. Cool. We live in an age where whatever you do, there's like 5 papers that do the same, unfortunately, which what made me stop working on post-training the last 5 months. These are other methods that are, in the same flavor from around the same time. So I know maybe it gives confidence that there is something here, but it's kind of like a little annoying that everyone is doing the same thing. And this is AI2 Scholar. This AI2 Scholar thing? It's kind of cool. So they found a few more papers that I didn't know about that also do the same thing. Not the same thing, but like at a high level. Cool. Yeah, I have less time than I thought, but let's go for it. So this is the offline case. I'll give some background. DPO is like a very influential off-policy alignment methods where the idea is the following at a high level. When we train a reward model, right, like this was the objective to kind of like maximize the log probability, preferring the preferred and dispreferring the dispreferred. So in DPO, they show that you can reparameterize, like express the reward as a function of the policy, and like these normalization constant cancel out conveniently, and you get like this objective where this is like the implicit reward, right? Like you had the reward for the preferred generation, and this is the implicit reward according to the policy, which is log pi of the generation divided by the probability according to the initial model. And why was DPO motivated? Because it's simple. It gets rid of the reward model, and it doesn't do reinforcement learning. It's just like supervised classification. So these were 2 things. But very quickly, people noticed that there are issues with DPO. And I already talked about that, what's called likelihood displacement, where the probability mass of the model moves away from both the preferred generations and dispreferred generations. So just like as a quick thought experiment, there's a lot of bad policies that will get like, the best possible loss. So as long as you give like 0 probability to all of the dispreferred generations and non-zero probability to all the preferred generations, then the gap between the preferred and the dispreferred is like maximal, and you get like the best possible loss that you can get. But the probability mass could be outside of the training set completely, right? So it's not hard to convince yourself that that's true, right? Like if the dispreferred ones have 0 probability and the preferred ones have non-zero probability, then this is what happens. So this kind of like drives the probability of the dispreferred generations down pretty aggressively and also the preferred ones. Here's another kind of like thought experiment. Like if you imagine that your generative model is like a really stupid one, it's like a bag of word model. So like, you know, the probability of a generation is like the x of the dot product of the counts in some parameter vector theta. So here we have I love New York, right? So the counts is I1, love 1, New York 1. These are the parameters. You take a dot product, exponentiate, and normalize. Okay, so this is like a bag of word model. Then you can show that, first of all, there is like an upper bound on the probability of the preferred generation that is strictly decreasing during training. So you just like cannot be higher probability than that. So we show this in the paper. And secondly, that probability mass will kind of move to generations that only have words that appear more frequently in the preferred generation than the dispreferred. So here, you know, I love New York, I like New York. It will move probability mass to love, love, love. Okay? And we'll move probability mass away from I in New York and stuff like that. Again, you might say that's natural, but I know if you have preferred I love New York and dispreferred I like New York, maybe you shouldn't learn anything about I in New York, but their probability goes down. And there's like interesting theoretical work from Razin et al. That kind of like characterize this even more carefully and kind of like show that if the representations of the preferred and dispreferred are very, very similar, then you get like this property of like reducing probability on the preferred generations. Okay, so this is not good. Here are papers on this phenomena a lot. Here are papers that the AI2 scholar found about this phenomena more. Okay. But I just want to point out as like a side thought that what do we expect? What do we want from this contrastive objective? I mean, like if we wanted probability mass to go to the preferred generations, just like maximize the probability of the preferred generations. So suppose that's not what we want. Like we kind of think that, you know, the preferred generation is something and the dispreferred generation is something. They have some common things. Maybe they're good, maybe they're bad. But like this part is better than that part, right? Like it's a contrastive loss. You want to like specifically pinpoint like the differences. So there's been more and more work on kind of like on that, I think. So there's anchored preference generation that was recently proposed where they kind of like explicitly generate minimal pairs and show they can get benefit from that. And I also saw on the Llama 3 tech report that they took like the preferred generations that are outputted by the model and manually humans kind of like minimally changed them to be even better. So I think maybe like there's a lot of like things to do in terms of like data. And maybe when you have minimal pairs, like the learning signal is better. But like, you know, maybe like the log probability of the preferred going down, maybe that's fine as long as like it's going to other good things. But in fact, it's not. It's like really crap. Okay, so in the time I have, I will say like what this work was about. And the idea is the following. It's pretty simple. DPO said, you know, let's get rid of the reward model and let's use supervised classification. We are saying, use your reward model. Reward models are great. You know, like, I don't think that like training a reward model is such a big deal. It complicates things by a bit, but not by much. But you get a lot of benefit from using the reward model because you can do a lot of things. First of all, you can like, when you train it, like regularize it, use inductive bias as much as you want, and do a lot of things to make sure that it's more regularized than just like preference pairs. In preference pair, you're saying, you know, y plus is preferred on y minus, right? Is better. Like probability 1 on y plus, probability 0 on y minus. But if you ask like 100 people, probably 80 will say y plus is better and 20 will say y minus is better. But we don't have this data. We have very finite sample data. By using reward models and regularization, you can get like these more soft effects where some pairs are, the distribution is different. Like here, I really think y plus is better, but here maybe I'm not so sure. So you can get like these very nice regularization effect from the reward model. And secondly, you have a lot of freedom. You can use like, you know, you don't have to tie the policy and the reward. The reward model can be huge. The reward model can be an ensemble. The reward model doesn't have to be Bradley-Terry. It can take X, Y1, and Y2 as input. You have a lot of flexibility. So we're saying use your reward model to annotate the offline data and then do DPO. Roughly that. That's the high level. So this is the objective that we propose. And as you can see, it looks pretty similar to DPO. This is like the term in the log sigmoid of the DPO. But instead of like maximizing the log probability of this term, you're assuming that you have some reward model, R star, that says how much better is Y1 than Y2. And you're just like training your policy to match that difference. And this difference might be different across different pairs, right? And you won't get this like really bad optimum at infinity. And the reward model can be many things. So this is the objective. Any question? It's like the most important part. Cool. And here are the advantages as I described them. The probability of the dispreferred response no longer goes to 0. You can use the reward model as like a distillation source because the reward model is discriminative, right? Verification is easier than generation, though the reward model can have like distillation effects. You can use a bigger model, a prompted model. You can do a lot of stuff. So this is like gives a lot of flexibility. That's her point. Yeah. Okay. And I'll say like in 1 minute something about pessimism, which is the following. So like the reward model that you train, it might be bad. You might have some bad luck and it's bad. So what you can do is kind of like define like a family of reward models and try to train your policy to be good with respect to all of them. So you change like the RLHF objective such that you're trying to have high advantage compared to the beginning with respect to like a family of reward models. You want all of the reward models to think that your policy is pretty good. That's the idea. And Adam, the first author of this work, cleverly showed that if you do some math, then this turns out to be like you can turn this into this offline objective that basically says you try to make your policy match one of these set of things, but out of those, you're going to choose the one that has the lowest forward KL divergence with respect to IREF. So that's the outcome that you get. And simultaneously, there were 2 other papers that have a very similar derivation, so it's probably correct. Cool. So that's the high level idea of pessimism. I have very little time. More than that, you can, and then you relax it with Lagrangian relaxation and you optimize it with some way that I'm not going to get into. More than that, if you kind of like, as I said, if you know that like long outputs are a problem or something, you can train multiple reward models. Maybe you train one reward model where a longer generation is preferred and one reward model where shorter generations are preferred. And just make this part of like the set of reward models that you want all of them to kind of like think that your policy is good. So this is like another thing that we check. Cool. So any questions here? I know it was fast, I'm sorry. But like the main point is like distillation to a reward model. And you can like do this with respect to a family of reward models to get like a little bit more robustness.
A quick question, actually. So we had the speaker from the other paper you mentioned come a couple weeks ago. Which paper? The Reza, the Princeton one, the theory of this.
Oh, cool.
There was this question that came up about like how doesn't the PPO objective have the same bad little optima? And the discussion was about like why that's not a problem in PPO. And I think kind of is your claim here that the reason that doesn't come up in practice is because people are implicitly regularizing the reward model? Yeah. Okay.
I think so.
Okay.
And there's the IPO paper, Azar et al. He has like a whole paragraph like rambling exactly this point, which
that paper unreadable, but I know that paper are hard to read.
Sure. So I'll send you a paragraph.
Okay.
I have it here, but I didn't. Okay. Yeah. So I think so. There's a lot of like regularization going into the reward model training.
And that's not specified in the math. It's just kind of in the way people do it in practice, or.
I mean, we know that the optimum for both are the same. I mean, I think like the behavior is different also. As I said, because of like coverage issues, right? Like the on policy quickly kind of like goes very away out of distribution. And the problems are it just like finds features that it can just like drive up and up and up. And that's the type of failure that you see. But in DPO, you don't see that. Yeah. I don't know. Maybe it falls out of the mass. I don't know.
Yeah.
We don't have time. So maybe you'll believe me that we get some gains. I have to say, just want to say 100%, like the gains are not as high as we expected, which is why we were rejected from NeurIPS, but I think they're real. I also think there's like just advantage in being more robust in the sense that model selection is easier. We assume an auto eval model for model selection, but that's not how it is in real life. In real life, you need humans or something, and this makes like everything much more stable. But again, I'll skip over that. These are other works that do something very similar. And these people that do something very similar to us, got much better empirical gains that we did. So maybe they're just like smarter than us in that respect. So the conclusion, offline mesas were shown to be susceptible to degenerate outputs. Our proposal is just to bring back the reward models, use them, just have like the best reward models you can to distill from, and you can still do offline alignment. That's fine, and you can get definitely a lot of robustness gains. I had some discussion that I'll skip. Thank you. People with red are like core contributors, and Jacob and Adam are the first two authors of the papers.
Okay, we have time for one or two questions. Yeah. Okay.
So I got one. If it sounds like kind of the magic bullet to both is an ensemble method, do you think that is kind of the final iteration of that, or do you think there's some better architecture out there, like a mixture of experts or?
I mean, we got positive results also without the ensemble. So even with a single reward model, but like defining like a ball around that, as long as you get like reasonable loss with respect to that reward model, that also brings some positive effects. So it's not like that only ensembling made it work. I think in general, like ensembling buys you something, but then at some point you just want like a better reward model, like in general. So I mean, my experience has been that it's useful, but there's like some ceiling on that.
So that's basically the llama process, like gradually add more data and retrain your reward model.
Yeah, I think the llama thing is just about making sure that the reward models is in distribution for the policy to avoid like these catastrophic like emoji ball bullets long outputs.
Okay, let's thank you.
Thank you.